Hi. Yes, Oscar. Hi, John Paul. Just I thought I'd go over this by video because it'll be easier than explaining. But good question. You're choosing quite a tricky one. So, the nice thing is actually when you do catalysis questions, if they're going to ask a long marker, they often kind of choose something like this. So definitely worth going into. So you've got redox reaction in an aqueous solution between acidified potassium permanganate, so that's going to include K plus ions and MnO4 minus ions, and sodium ethane dioate is autocatalyzed. Okay, so autocatalyzed, that means a product of the reaction is a catalyst. So the reaction will get quicker as it goes on until stuff starts to get used up. And sodium ethane dioate, well, sodium's easy, that's Na plus ions when you're in a compound. And then ethane dioate, so if you think about ethane, it'd be based on 2 carbons. A dioate is basically the negative ion of a carboxylic acid. But di means you've got 2 of them, so basically each carbon is like that. And is autocatalyzed. Now the thing is, the dioate ion, you kind of need to know actually what that goes to make. MnO4 minus ion, you need to know what that goes to make in a redox way. So the dioate ion, C2O42 minus, can go and make CO2. And you look at the ratio is already right. So what's the difference between C2O42 minus and 2CO2? Well, basically just C2O42 minus has extra electrons. So if you're going to do that, that's going to release those couple of electrons. And this is why you often see it in redox context. And then MnO4 minus. Oscar's just speaking to his monkey on the iPad. MnO4 minus, well, you basically need to remember that makes Mn2 plus when it gets reduced, and we'll work out the half equation for that soon. So that's kind of like those are the chemicals, and that's kind of what you might be expected to know from the first sentence, and then what might be able to work out with this autocatalyst stuff. Well, look at the products of these reactions. So there's going to be one reaction, because we've got it in 2 halves here. CO2 unlikely to be a catalyst. What catalyzes stuff is transition metal stuff. So Mn2 plus must be this product that's a catalyst there. So that's what you're trying to think of it as a catalyst. So we've got an equation for the redox reaction. So what we can do is basically add these together, and once we've made the full half equations, identify the species that acts as the catalyst. It's the Mn2 plus. So you're looking for a product that's a transition metal ion, and that'll be the catalyst. It's really unlikely that you have more than one to choose from, but if you ever did, go with your gut instinct on that. Go with one that you recognise. Explain how the properties of the species enable it to act as a catalyst in this reaction. Okay. So this is a little bit. This is all to do with the transition metal's variable oxidation state, and actually we're going to explain via the use of equations here. So we're going to let's look at all the equations. Then I'll tell you how to plan an answer for that. So here, first of all, well, we haven't fully finished off my manganate equation. So permanganate plus a certain number of electrons goes to Mn2 plus. Well, I know manganese's oxidation state in permanganate is 7, and I can work it out by thinking 4 times minus 2 is minus 8. To get that to minus 1, I need 7 plus. It also says it in the name. And I'm going to go to manganese 2 plus, which is obviously oxidation state of plus 2. So I need therefore 5 electrons to go from 7 to 2 down. It needs to be a 5 electron reduction. So electrons on the left hand side, 5 of them. Where's the oxygen's going to go? Well, I'm going to have to add 8 H pluses to soak up those 4 oxygens and make 4 waters. So you're probably used to that one already. Now, in order, basically how this all works is manganese gains 5 electrons from ethane dioate ions, and then goes to make manganese 2 plus. Now, when you look at the catalyzed version, actually, instead of manganese 2 plus can actually go and make manganese 3 plus. So if you look at the let's do it in a different color now. If you actually look at this catalyst couple, you need to also remember that manganese 2 plus can go, and because they don't tell you that, do they? No. So yeah, it can go and make Mn3 plus, and so you should be kind of happy with ions making 2 plus and 3 plus commonly transition metal ions, not any old ions. This equation can happen. I'm going to write it like with a reversible arrow, but it doesn't mean it's a really reversible reaction. It just means it can go in both ways. You can oxidize manganese 2 plus to manganese 3 plus, or you could reduce manganese 3 plus to manganese 2 plus, and this is kind of how the electrons shuttle through from the ethane dioate to the manganese oxide ions. They actually go via this Mn2 plus, which turns into an Mn3 plus. Turns into Mn3 plus when it gives an electron to the manganate ions, and then on the other side it can go and so if it's giving electrons away, that makes Mn3 plus, and then Mn3 plus can go and combine with C2O4 minus ion and steal its electrons to make Mn2 plus again. So we'll basically look at how that works. So a few things to do that you haven't quite managed to do yet is the overall. So overall here, overall equation. You don't need to consider the catalyst because that would never exist in the overall equation. So what we're going to do is we're going to add equation A and equation B together, but we've got 2 electron change in A and 5 electron change in B. So we're going to add 2B to 5A, and then we'll have a 10 electron change in both ways. So let's do A very carefully now. So 5C2O4 2 minus. Goes to make 5 times 2 is 10 CO2 and 10 E minus. I'm going to draw them in, even though I know I'm going to cancel them later. And then 2B, I've got to try and fit everything in, so I should have left myself more space. But 2B is 2MnO4 minus. Then I'm going to cheat by going to the left-hand side. 10 electrons, 2 times 5 is 10. And 2 times 8 is 16H plus. You see how you've got to be really careful that you're timesing the right things by 2 or by 5 or not forgetting to times them by something. This is why I draw that at the top, the 2B plus 5A, and I also just try to be careful about it. So 2B, Mn2 plus, that means you're going to have 2 Mn2 plus. And 2 times 4 is 8H2O. You want to check this balances and everything, but most importantly, you need to cancel out the stuff that cancels out. So electrons, you can just strike through like that, that's fine. Or maybe more obviously with the cross. 16H plus, nothing cancels there. 5C2O4 doesn't cancel. 2NO4 minus doesn't cancel. So that should be your overall equation. Redox species is Mn2 plus. So what we're going to do is we're going to twin this Mn2 plus with something that, so Mn2 plus itself gets oxidizes, loses that electron, so it reduces the other thing. So what's getting reduced is the manganate. So we're going to twin equation B with equation C for catalyst. And now this time we're going to do 5 lots of C to make it a 5 electron change, would combine with 1 equation B. And what we'll get here is basically an equation for half of the catalytic process. So first of all, manganese 2 plus would react with a helicopter. Yeah, sorry, manganese 2 plus would react with manganate ions in order to provide electrons. So 5 of them would be needed, and reduce the manganate ion first. So these are oppositely charged ions, 2 plus and a 1 minus manganate ion, and a 2 plus Mn2 plus. So they're not going to repel each other on the collision in. So this is quite a favourable thing to happen. So let's go different colour again. And let's add these things together. So that would be one of the top ones. So 1 of B, MnO4 minus. Plus again, I'm going to write the electrons in and then cancel, because it just makes me make sure that I'm doing things correctly. Leave space for C. 5 of C would be 5 Mn2 plus. Goes to make 5 Mn3 plus. I'm sticking with the Mn because I really don't want to forget this 5 multiplication. And then I'm going back to my one that I didn't need to multiply, which is B plus Mn2 plus. Plus 4H2O.
Helicopter.
Yeah, helicopter. Now, in order to cancel things, now I'm going to be really careful. 5 electrons, always, they're going to cancel. But what else? MnO4, no, there's nothing that's exactly MnO4 there. H plus, no, there's no H pluses, but 5Nm2 plus, well, I do have 1 Mn2 plus on the right-hand side. So really, overall, I'm not using 5 and making 1, or maybe I am, but I'm overall using 4 up. So that should be my overall equation. Now, this is basically the first... A plus B here is the first step of acting as a catalyst. So when you're wording your reaction, your answer here, you want to say, okay, here Mn2 plus, what's it? Mn2 plus has reduced it is a reducing agent for the manganese. So reduces MnO4 minus in first catalytic step. See how the first step had 2 half equations. That's fine, it's still one step. There's one overall reaction now. I know it gets a bit confusing having all these half equations and all these full equations. So really you've got one overall uncatalyzed equation, which means you have 2 steps of catalysis, and each step of catalysis both have 2 half equations. So you can get lost in equations if you're not careful. Alright, now quickly on to the next step, as I'm sure you're raring to do now, because I've blabbed on a little bit too much. So let's go for a lovely blue. So, well, now you've produced lots of Mn3 plus. Okay, so Mn3 plus now can go back to Mn2 plus if it steals an electron from somewhere else. So how are we going to reform the catalyst? It's going to reform the catalyst by Mn3 plus taking the electrons from C2O42 minus. Now again, C2O42 minus. Yeah. C2O42 minus is negatively charged and Mn3 plus is positively charged, so when they collide, again, not a bad thing. So how am I going to mix these things up, these 2 equations? Well, now it's just going to be 2 lots of the catalyst half equation, 2C plus 1A, because it's a 2 electron change. So here on the left-hand side, well, Mn3 plus is what we're starting off with, but it was 2 of them, wasn't it? So 2 Mn3 plus. It's going to make 2 Mn2 plus.
Okay.
And that takes in 2 electrons. Now I need to go and add my A plus C2O4 2 minus ion. And then goes to make 2 CO2. And again, those 2 electrons there. So as always, electrons should cancel, because that was the whole point in us choosing these coefficients, the cross multiplication method, and then we just need to check that I've got nothing else. Now, Mn3 plus is not the same as Mn2 plus, so that's fine, they don't cancel. C2R42 minus is not the same as CO2, so that doesn't cancel either. And check the charges, 6 plus there, 2 times 3 plus is 6 plus. Minus 2 is going to be 4 plus overall, whereas 2 times 2 plus is 4 plus with nothing else, so that's all good. Good, so your wording here, for the wordy bit here, is, well, here, Mn3 plus oxidizes C2O4, is that you said it? Oh, you've got Bixby on, Oscar, sorry, 1 second. Should I fix it? Oh, it's just telling you it's low battery. There you go. Sorry about that. You want me to change it?
Oh.
Okay, good one. Here you go. Where was it? Mn3 plus oxidizes C2O4 plus 2 CO2. In the second catalytic step. And this is what reforms the catalyst, that might be something to do. So explain how the properties of the species enable it to catalyze in reaction. So really probably going to, I would if you're not writing out these equations, I've done it in a very much Bayern equations way, maybe that's a bit overkill, but look at the mark scheme. But you definitely want something about how it gets, the manganese itself gets oxidized in one step while it reduces the permanganate, and then gets reduced again in the other step when it oxidizes C2R42 minus. So that would be kind of what you're looking at there. But again, go and look at the mark scheme because that hopefully be useful. Now sketch a graph. Sketch. I don't know what those words were, but sketch a graph of how concentration of MnO4 ion varies with time. Now, this is a little bit of a learning thing. Really quickly before I get in trouble with my 2-year-old. So that's going to start off slow because it starts off relatively slow. If you're going to get a catalysis, it's going to speed up. So if this is the concentration of MnO4 minus, it's a reagent in the overall reaction. You do look like ketchup and eggy bread. You're right, Oscar. So your MnO4 minus here is a reactant, so it's going to go down. Its concentration is going to go down over time, but it starts going down very slowly because it's uncatalyzed. And then what happens is the Mn2 plus that you form, the one that's in the autocatalyst for the process. Well, that's going to build up, and then if you've got your catalyst there, suddenly the catalyst route becomes available, and it goes quicker. So it goes quicker. Steep graph means rapid rate. And then, but at the end of the day, we're going to lose our reagents of MnO4 minus and C2O42 minus. So as those concentrations go down, then the rate of reaction will slow again, and it will tail off. Tail off there. Ignore that last little bit. So yeah, autocatalytic reactions. You should kind of talk about the uncatalyzed, slow, catalyzed, quick. And then slowing down because of concentration of reactants and concentration of products diminish. It's a nice word, isn't it? If I could spell it. Yeah, good. Any other questions? Just keep asking them. And good luck.